Welcome back. In this section, we're going to look at fundamental identities, and it's going to take a lot of work to memorize these things. So I'm trying to make it silly, but it's not. It's not. You have to memorize these, and some of them will be familiar to you already, which is the good news. The bad news is you have about probably 25 more to go, so we better get to it. In the previous sections, we've studied the trigonometric functions from the geometric perspective. It's time to look at the algebraic approach to trigonometric functions, which is often used in calculus. We need to learn how to simplify and prove or disprove equivalencies of trigonometric expressions using identities. These are very important skills that you must build to succeed in calculus. Keep in mind that you need lots of practice. There are different ways to approach a problem, and by practicing, you'll be able to find the shortest way. So far, we've seen the following identities. You need to memorize these, and there is more to come. By the way, what's an identity? Let's review the ones you know already, and possibly even without even realizing it. An identity is something that morphs, so you can write it in two different ways. The simplest thing I could compare it to is if you have, say, 3 plus 2 on one side of your equation, you know it's equal to 5, but you're writing it in two different forms. With identities, we know that the cosecant of x is equal to 1 over sine, the secant of x is 1 over cosine, the cotangent of x is equal to 1 over tan x. And depending on how you say these, you want to make sure that you're keeping your x's with the functions. This is something I see happen a lot when students become frantic or feel like they're under a very short time limit. They start dropping the x's. So don't forget to put those x's or thetas or whatever in there so that they make more sense. The fourth one is tangent of x, which is equal to sine x over cosine x. And lastly, cotangent of x is cosine x over sine x. So these are ones you should have memorized already. These should be very easy to find in your brain on demand. And if they're not, they should be. So keep working on it. If you need to, I would say highlight this so that you can quickly go to your notes and say, okay, reciprocal identities, I have to memorize those. The Pythagorean identities you should know already. We know that from previous sections, sine squared x plus cosine squared x equals 1. Tangent squared x plus 1 equals secant squared x. And 1 plus cotangent squared x equals cosecant squared x. Again, all of these you need to be able to memorize, and you should be able to derive the second two from the first one. And then the next one we have is the negative angle identities. These are called even-odd identities, and this just says that if you were to put a negative angle inside the sine function, it's equivalent to the negative sine x. This becomes more obvious and useful when you get to calculus, but for now, if you were to graph these two functions, sine of negative x and negative sine of x, you would see that they were equivalent. Same with cosine of negative x. That's equivalent to just plain old cosine x. And tangent of negative x is equal to negative tangent of x. So those three you also need to memorize even if you haven't really seen them yet that much. Using the Pythagorean identities, you need to be able to recognize that sine squared x equals 1 minus cosine squared x. And then we also know that cosine squared x equals 1 minus sine squared x. Same thing with the other two. So you have to be able to take each one of these terms and be able to move it back and forth to each side of the equal sign. And if you can't do that, you need to practice it. Now remember I mentioned that if you have an identity, it's kind of like saying you have 3 plus 2 equals 5, where one side does not look like the other. But they're equivalent. When you are simplifying a trigonometric expression, sometimes it's easier to rewrite everything in terms of sine and cosine. Another option is to get a common denominator. And finally, remember to only use substitution. When I look at this very simple identity, I can just simplify the left side, 3 plus 2 equals 5, and so I have 5 equals 5. This proves that it is an identity. It is identical on both sides of the equation. That means that if I want to look at something that's being claimed to be equal, and it says prove or disprove, I only work on one side of the equation. Some instructors will let you work on both sides and simplify one side until it looks like the other side, and then maybe you get stuck, so then you can work on the other side until they both look the same. But I am somewhat of a traditionalist when it comes to this, and you can only work on one side of the equal sign, and you need to show that you can morph that one side to look like the other. So one of the ways you can do that is by picking the side that looks it sounds silly, but looks the ugliest, and leave the other side alone and morph the ugly side to look like the nice looking side. And that's all relative, of course. But if it helps you, say, I'm working on the right-hand side, and literally put that right under the side you're not supposed to touch, because it'll help you restrain yourself, I guess, because if you solve this thing, you'll get 0 credit when you take your test. I am so serious. This is how important this is. So you must never solve an identity. That's why there's a reason why it's bolded and capital letters and over and over stated here. This is so important to show competency and confidence around simplifying identities. My rant is over. Now I will show you how to simplify this identity. Notice that I have 2 different denominators, and the only way I could simplify this further is to get a common denominator. The way I would do that is to multiply both of these by their conjugate, which is 1 plus sine x on the left fraction and the other one is 1 minus sine x. Notice that when I multiply by the same thing in the numerator and denominator, it's going to be equivalent to multiplying by a funny looking 1. And so I'll have 1 plus sine x over 1 minus sine squared x minus 1 minus sine x over 1 minus sine squared x. Now that my denominators match, I'm getting closer to what I need. I need it to look like the left side, which is 2 tangent of x secant of x, and so I'm going to combine the numerator and denominator. Notice I have to subtract the entire second numerator, so I'll have 1 minus 1, and I'll have plus sine x plus sine x all over 1 minus sine squared x. Do you see how I have not touched the left-hand side here? I am not solving an equation. I'm trying to get the right side to look like the left side. And now my 1 minus 1 goes away. My sine x plus sine x becomes a 2 sine of x. And then in the denominator, I just have 1 minus sine squared x. Now, if we think about the left-hand side, notice I'm not changing it, I'm just analyzing it here. It's kind of like a little kid shaking the presents before Christmas or something. If you have tangent of x, it's going to be equivalent to sine x over cosine x, right? And secant is 1 over cosine of x. That's interesting. And we have a 2 in the numerator. So if I look at what I have over here, I need to figure out how to get 1 minus sine squared x to look like cosine squared x. But what do we know about our Pythagorean identities? We know that 1 minus sine squared x is equal to cosine squared x. So I can take what I know and I can say, but this is equal to cosine squared x. And then I do a substitution where I have 2 sine of x over cosine squared x. And then I can break it up where I have a 2 sine x over cosine x times 1 over cosine x, which is equal to 2 tangent of x times secant of x. And ta-da! You have shown that you can make the right side look like the left side. And so you can put a little box here that says, you've proved it. This is just a formality, but some people will say QED. Some people will put a little box here. It just means that it has been shown as required. Very formal as a mathematical process, and you need to make sure you do this process. Now, you might be asking yourself, could I have done this to the left side? Absolutely. You would just have to work the opposite direction. So instead of picking the right side to simplify, you would have picked the left side and you would go through this process, but you'd work your way up to get to here. It's a little harder to expand something out. Usually it's easier to simplify. That's just how we've kind of been programmed in math. But if you think the opposite way and it's easier for you to expand the left side, that's totally fine too.